Welcome to Grade 11 Artificial Intelligence. In this module, we study the breakthrough that powers modern language technology, the transformer, and its idea of self-attention. We'll see why reading one word at a time held machines back, how attention freed them, and how models like BERT and GPT learn language before they ever see your task. Here is our plan for the lesson. We'll start with the problem of reading word by word and meet the core idea that fixed it, self-attention. Then we'll trace the whole transformer and see how text is first broken into tokens. Finally, we'll compare BERT and GPT and understand why we pre-train a model first and only then fine-tune it for a task. Before transformers, language models read a sentence one word at a time in order. These recurrent models carried a memory forward, step after step. Two problems followed. First, in a long sentence, the early words faded by the time the model reached the end, so distant connections were lost. Second, because each step had to wait for the one before it, the work could not be done in parallel, and training was slow. Yet meaning often depends on far apart words. The word bank means something different in the river bank and the savings bank, and only the surrounding words tell us which. What we really want is for every word to look at every other word directly. That is exactly what self-attention provides. Self-attention is the heart of the transformer. To understand one word, the model lets it look at every other word in the sentence at the same time. Take the word sat. The model asks how relevant each other word is to understanding it. It gives each word an attention weight, shown here by the thickness of the connecting line. Cat and mat receive high weights because who sat and where give sat its meaning. Words like the and on receive low weights. The model then blends the words together, weighted by attention, into a richer representation of sat. Crucially, every word does this for itself, all at once, so nothing is forgotten and the work runs in parallel. Now let's see where self-attention sits in the full model. Follow the flow upward. The tokens enter at the bottom. Each token is turned into an embedding, a list of numbers that captures its meaning. Then comes self-attention, where every token weighs every other token, as we just saw. After attention, a feed-forward step transforms each position on its own. This pair, self-attention then feed-forward, forms one layer, and the model stacks many such layers, one on top of another. Each layer builds a deeper understanding than the last. At the top, the model produces its output. But before any of this, the text must be turned into tokens. A model never sees letters or whole words the way we do. First, a tokenizer breaks the text into small pieces called tokens. A common word becomes a single token, while a rare or long word is split into several pieces. The Kinyarwanda word umunyeshuri, meaning a student, may split into a few subword tokens because the model learned its pieces from data. Each piece is then mapped to an integer, an identity number the model can work with. This matters in practice. The number of tokens decides how much you pay to run the model and how much text fits in its context window. Now we can put a whole system together, BERT and GPT. Two famous families built on the transformer show two styles. BERT is an encoder. It reads the whole sentence in both directions at once, which makes it strong at understanding. It is pre-trained by hiding or masking some words and learning to predict the missing ones from both sides. GPT is a decoder. It reads left to right and is pre-trained to predict the next token, which makes it strong at generating text. Both share one powerful recipe: pre-train, then fine-tune. First, the model learns language in general from huge amounts of text with no labels. Then we fine-tune it on a small, labeled dataset for one specific task. This is why a single pre-trained model can be adapted to so many jobs, cheaply. These ideas already shape tools people use every day. In Rwanda, transformer models power Kinyarwanda translation and chat assistance, helping technology meet people in their own language. In education, a tutor can explain a hard idea in the learner's mother tongue. Across the United Kingdom and Europe, a single multilingual model can support dozens of languages at once. In the United States, search engines and assistants use these models to summarize long documents. And in healthcare, they help pull key facts out of clinical notes. One architecture, pre-trained and fine-tuned, serves many very different communities. Before we recap, let's clear up the common misconceptions. First, self-attention is not a memory carried forward. It weighs all tokens at the same time in parallel. Second, tokens are subword pieces, so one word can become several tokens. Third, BERT and GPT do different jobs. One is built to understand, the other to generate. Fourth, pre-training learns from raw, unlabeled text, while fine-tuning uses a smaller labeled dataset. And finally, attention is powerful but not free. Its cost grows with the square of the sequence length as order n squared. Hold these distinctions, and your understanding will stay sound. Let's gather the key ideas. Reading word by word loses distant context and blocks parallelism. Self-attention fixes this by letting every token weigh every other token at once. A transformer stacks self-attention and feed-forward layers, one on another. Text is first split into subword tokens, each a number. BERT is built to understand, while GPT is built to generate. And both follow the recipe of pre-training on raw text, then fine-tuning for a task. Now, let's check these ideas with 3 quick questions. Here is the first question. What does self-attention let each token do? It lets each token look at every other token in the sequence at the same time and weigh how much each one matters. The token's new representation is a blend of all the others, weighted by attention. Question 2. A rare word is broken into 3 tokens. Why does a model split words into subword pieces? Because a fixed vocabulary of subword pieces can build any word, even one it has never seen, by combining pieces it already knows. This keeps the vocabulary small while still covering rare and new words. Last question, and it ties the module together. You must classify Kinyarwanda product reviews as positive or negative, but you have only a little labeled data. What is the efficient approach? Take a model already pre-trained on large amounts of text, which has learned the language in general, and fine-tune it on your small labeled set. A model like BERT fits this understanding task well and needs far less data than training from scratch. Excellent work. You now understand why reading word by word held machines back, and how self-attention lets every word weigh every other. You can trace the transformer, explain tokenization, and tell BERT from GPT in the pre-train then fine-tune recipe. In the next module, we'll turn from language to vision with advanced computer vision methods. I'll see you there.